Today we're going to look more into Chapter 9 through polyprotic acid-base systems. Specifically, we're going to focus on a set of new equations that are going to tell us a bit about what the solution looks like in terms of which species is there in the largest amount, and moreover, how you can calculate the relative amounts as a function of pH, which is a pretty powerful tool. To get your brain going on this thought, I found this information about uric acid. It's diprotic. There's only 4 H's shown. There actually are only 4 H's in the molecule. I believe that one of the K's applies to one of these two species and then the other one applies to this. It's not super important. What you need to know is that this substance, as it's written, is not terribly soluble in water. And that's dangerous because uric acid shows up in the body exactly where the name suggests it does. And if this substance doesn't dissolve in water, it doesn't really dissolve in blood that well either, which means if it's in your system and it's in this form on the screen, then it's forming crystals in your body. And that's how you get kidney stones. At least it's one of the methods, which is really not good to have. So what will happen is the intermediate form, once it loses those H pluses, it becomes charged, and then it's really soluble in your blood, and that's a lot better for everyone. Doctors will sometimes measure the pH levels of urine to ensure that it's not getting too acidic, because if it gets too acidic, that's one of the indicators of risk for kidney stones. So it's really important to have a formula where you can say, that's the pH, that's the pH, that's how much there is, and that's the pH where I want to be worried about things, whether it be kidney stones or anything else that's going on in the body at the time. To relate this back to things we've seen before, this is the data from the leucine species that we've been working through in class, and obviously we solved all of these already, but I just want to make a point of a couple things. What we see is when you start with the fully protonated version, the fully protonated version is still the substance that is in highest concentration as you look across these three. Same can be said for the intermediate, and the same can be said for the fully deprotonated form. I believe that is a typo in your book, actually. That this is the most, like the largest amount. If you wanted to turn these into like a percentage, you would just divide all of them by 0.05 molar, which is the formal concentration. More importantly, though, is when you're looking at the data as it's organized on the table, we can actually look at all, we can actually look at all of the H2L species at once. And what we can say is as the pH increases, the amount of H2L decreases in the same 0.05 molar solution. Same thing looking at the pH increases, it looks like that the HL concentration goes up and then goes down, and then the L minus concentration actually steadily increases as pH increases. Which is interesting, because then the next logical question is like, well, what happens if the pH is 4, or what happens if pH is 7? And you can see like why it would be helpful to have a formula to let you do that. In order to not make this too terribly In order to not make this too terribly confusing, I thought it would be a good idea to step into a monoprotic system first. So I'm going to start writing, since it says systematic treatment, over there, on the side. I'm going to start writing the systematic treatment while I'm talking. But for this situation, we're talking about a standard monoprotic weak acid. And what ideally we want to do is not just figure out how much there is of everything given a pH. I ideally would want to write a formula such that the only variable is H+, and then I can plug in H+, and I can get a bunch of answers out, which is super useful. The thing that we're targeting is not the absolute amount of a species, it's more the relative amount of a species. As it says in the words over there, we're looking to calculate A minus over F, or HA over F. So going through our systematic treatment, it gives us this. I'm going to get rid of one of these. There's a really good reason why we don't want to be using the charge balance here. The charge balance is true, obviously, it has to be. But if we're dialing back up and down the pH, we're adding an acid or adding a base to do that. And that means you're adding charged species to your solution. So the charge balance, while always true, is going to be highly variable between these three solutions. So you don't really want to use it if you don't have to. But I'm going to go through the same process twice in order to get some answers. First, as it says in the top, I want to come up with something that says A minus over F equals, and the only variable is H plus. To do that, I see my two equations here. I kind of want to target getting rid of either HA or A minus. Since I'm targeting A minus, I want to get rid of HA. So I'm just going to rewrite the Ka expression in terms of HA. And when you do that, you get HA equals H plus times A minus over Ka. Substituting into the mass balance, you're going to get, oh, that's so messy. I'm going to try again. Substituting into the mass balance, from here on out, it's just algebra, so I'm going to factor out my A minus. We're going to get H plus over Ka. Oh, I shouldn't have an equals there. Doing great. Take 3. We want this to be parentheses plus 1 equals F. If we divide this over, what we're going to get, and I'm going to take the fraction that's there and I'm going to put it all together so that it's not so messy, we're going to end up with H plus Ka over Ka equals F over A minus. And as you can see, that's actually just the reciprocal of what we want. So if we flip everything, we end up with A minus over F equals Ka over H plus Ka, which is nice. I mean, the only variable there is H plus. You plug in H plus and you can solve for numbers. So what I'm going to do is, I think if we have that, it says for the last bullet, we might as well do it now, determine the composition of a 0.1 molar solution at pH of 3, 4, and 5. But the composition, I don't even need the formal concentration. If I'm just trying to solve for the fraction, it's always going to be divided by 0.1, or if you wanted the A minus concentration, multiply by 0.1. So I'm not going to worry about it. All you have to do is plug in. Ka is 10 to the negative 4.76. So for a pH of 3, I'll write it once. This is going to be equal to 10 to the negative 4.76 divided by 10 to the negative third plus 10 to the negative 4.76. And when you do that, what you get is a relatively small number. You get 0.017, which tells me that 1.7% of the solution is in that form. Well, no, I won't say that yet. That's coming up. If we then, oops, too many touches. If we plug in 10 to the negative fourth instead of 10 to the negative third with the same exact equation, as you might expect, it's the same numerator and the same part here, where we took this number and we actually decreased it. We went from 10 to the minus third to 10 to the minus fourth. The denominator goes down, so this number should go up, and it does. So if you grab a calculator, you should get 0.148 as your percentage. So now we're at 14%. And if you plug in 10 to the negative fifth, you actually get a sizable difference. We get 0.635. Which is a drastic change. So it seems like we've gone from this being 2% of the solution to 15% of the solution to 64% of the solution. So that should make sense. As the pH goes up, the amount of conjugate base should also go up. Yeah, I think that tracks. Let's go through the process really quickly for the acid. There's some similar steps going on, so I don't think I need to show them all. Rewriting the Ka again to target the A minus, though, A minus is going to be equal to Ka times the concentration of Ha over H plus. If we were to plug this back into our mass balance, what we get is Ha plus Ka times Ha over H plus equals F. We're going to factor out the Ha, and I'm going to do two steps at once to save a little space because I think I'm getting close to my head. We're going to say Ha times Ka plus H plus over H plus equals F. Divide over the Ha, and then you flip the whole thing, and what we get, and I'm going to write it over here, is Ha over F is equal to H plus almost wrote the Ka expression. H plus over H plus. That looks awful. I'm not happy. This pen is like lagging on me. I hope it's not doing it to the video right now. That would be unfortunate. H plus plus Ka. And I want to just point out something in the two formulas while I have them here. In the two formulas we came up with, our final formula here and our final formula here. It seems to me like in these two formulas, the denominators are actually the same. Funny how that works out. And then the numerators change, but you can see that the numerators actually kind of match up with part of the denominator. More on that later. So you may be thinking a step ahead of me. If the solution is 2% A minus, it kind of has to be 98% HA. I get where you're coming from with that, and I don't disagree with you. And so, I mean, you can do plug in instead of doing the expression that we have up here. If we were solving for the fraction that is in the form of HA at a given pH, all we'd have to do is go back to our calculator, and instead we change our numerator, and we just solve for that. And what we get, it does match up, 0.983. If you plug in a pH of 4, you get a fractional composition here of 0.852. And for the pH of 5, you do get 0.365. And as you can see, obviously they add up to 1. They kind of have to. That's the mass balance. But also, as the pH goes up, the amount of HA goes down. So what happens when Ka is equal to H plus? Well, I mean, it should be easy enough to solve, right? It's just some algebra going on. We know that A minus over F is equal to Ka over H plus plus Ka. So if Ka is equal to H plus, that gives us H plus over H plus plus H plus, which is 1/2. Similarly, if we were to plug in for the HA concentration as a percentage, we get H plus over H plus plus Ka, which if Ka and H plus are equal, you again get 1/2. But I feel like we knew that already, because when Ka equals H plus, that's a buffer. We know what happens when pK, that means, right, like that means that pKa equals pH. We've seen that before. But what this does open up the door to start talking about is we're going to bring back the alpha that we saw before. In previous chapters, we said that alpha was the fraction of dissociation. Well, keep in mind that we said, to solve it, we said do x over f. Sure, but x over f was really h plus over f in that solution. But also, from our systematic treatment, it was also a minus over f. So we've been using this alpha the whole time. We just haven't been calling it that. The alpha of A minus, the alpha of HA, we're going to define that here on out as the fraction, the percentage of the solution that is in that form for that species. So like I said, if you look at this from a buffering perspective, what ends up happening is when pH equals pKa, then it's a 50-50 mixture. If pH is greater than pKa, well, usually we said that that means, looking at this equation, if pH is greater than pKa, that means that this term is greater than 0, and so therefore A has to be greater than HA. And if pH is less than pKa, this term is negative, and that means HA has to be greater than A minus. This is consistent with what we saw back on with this data. Considering that the pK is equal to 4.76, that would be right in the middle here. And as we see, it crossed, like both of the numbers would cross over 0.5. So if we were to actually go graph this for a large number of data points, I mean, you could probably graph this on your graphing calculator, and the graph would come out looking like this. And as you can see, the fraction that is in the A minus slowly increases, well, not so slowly, but increases as pH increases, and the amount of HA decreases, and the two are equal to each other when pH equals pKa. They're saying this is a hypothetical pK equals 5, so that it lines up nicely. But what we would say is, therefore, with this information, we can kind of say the predominant form of your acid is either HA or A minus as the pH changes, and the tipping point is where pH equals pKa. That's pretty useful. But what happens when you think about a diprotic acid? I need a lot of room to write. So, first things first, we're going to write our mass and charge balance. Well, no. Our mass balance and our Ks. So we have our phthalic acid. This is where KHP comes from, and you can also make phenolphthalein out of it. But it's a diprotic acid. And the mass balance here would be H2P plus HP minus plus P2 minus equals F. The K's, I'm going to try and squeeze them up here because they might become useful. K1 is equal to H plus times HP minus over H2P, and K2 is equal to H plus times P2 minus over HP minus. So remembering what we did last time, the solution was to use the K expressions to get all of the species in the mass balance to be the same thing. So that you could like have everything in terms of H plus, that species, and Ks. So I'm going to give you a minute now because I've done a lot of talking. I want you to pause the video because at this point you have enough information in front of you. I want you to try and figure out what this expression would look like. I'm serious. Go ahead and pause the video, like take a few minutes and do the algebra, because if you do the algebra, I think you'll have a better understanding of the steps that I'm taking. Did you pause it? I guess, should I ask YouTube Analytics to see if that's a thing? I'm not going to download Edpuzzle. That's too much. If you paused and you worked, great. If you didn't, I still want you to. Please, try it. This is your time to learn. Okay, if you're stuck, I'll give you a good hint. The first thing that you should do before we start is we should actually multiply these K values together, because this will give us an expression that puts H plus and P2 minus and H2P all in one expression, which makes our lives a lot easier. Okay. In order to solve for H2P over F, which is alpha H2P, we want all of our expressions in the mass balance to be H2P. So, we're going to use K1 to substitute out for HP minus in terms of H2P. So that should give us, I wrote this down so I wouldn't have to do this. Yeah. H2P times K1 over H plus. And then for the second one, we want to put P2 out in terms of H2P. So we're going to use our derived K1, K2 expression, which should give us, it should give us K1, K2, H2P over H plus squared, and that equals F. Hopefully you know where we're going next. We're going to do the same exact thing we did last time. Factor out the H2P that's present in all three of them. Divide it over, and then take your three terms and put them together. So I'll show it here this once. H2P, we're going to factor out. We're going to have 1 plus K1 over H plus K1, K2 over H plus squared equals F. So we're going to mush that term in the middle. We're going to put it all into one fraction to make our lives easier. I think our common denominator needs to be H plus squared. So what we get is H plus squared plus H plus times K1 plus K1, K2 over H plus squared equals F over H2P, which is almost where we need to be. We just need to flip it, and we get, touched the wrong button again. We flip it, and we get, we get an awful looking alpha. No. What we get is H plus squared over, I need a lot more space, H plus squared plus K1 H plus K1 K2. So using this is really helpful. Using this, we can just plug in different pH values. So it says in the slides, I want to figure out what happens at a pH of 2, 4, and 6. Like we saw with the fully acidic form before, I would assume that the fraction will slowly decrease as H plus increases. Sorry. The fraction would decrease as H plus decreased as pH increases. There we go. Which does happen. Just to write it over here, at a pH of 2, 4, and 6, the fraction ends up being 0.899, so almost all. Yes, that does work. At a pH of 4, if you plug in, you should get 0.079. So going from pH of 2 to pH of 4, you go from 90% of the solution to 8% of the solution. And then for pH of 6, it's 0.000182, which is almost 0. Which we've said before. When you're in a basic solution, or when you're starting with the base, the fully protonated form is essentially nothing. We've said that before. So this is all kind of connected. I like that. All right. So to take a look at the intermediate form, we would basically have to do this whole process again. So I'm going to hope that you wrote down K1, K2, and the mass balance, and the K1, K2 expression. In fact, I probably should tell you again to pause and go try and do this yourself. That would be a good choice. That would be an excellent choice. Please go do that now. Are you back? Good. Hopefully you thought about it a little bit at least. If you didn't, well, I'm going to go through it anyway. So let's start. I'm going to start by writing my mass balance again. And then now we're going to target HP. So we're going to use K1 and K2 to substitute out H2P and P2 minus. In doing that, what I'm going to end up with is, I think using K1, what we end up with is, nope, that one. H plus times HP minus over K1 plus HP minus plus HP minus K2 over H plus equals F. So again, we're going to factor out our term, and then we have to put it together, but this time hopefully you can see that the your common denominator is actually going to be K1H plus. So what we should end up with is H plus squared plus K1 times H plus K1 K2 divided by K1 H plus is equal to F over HP minus. If you need to see how these steps happen, I'd suggest going back to the H2P example to see how I got from the second step to the third step. To get from the first step to the second step, we're just using rearrangements of the K1 and the K2 expression. So hit the pause button, go back, follow these steps, because this is the important part. If you flip this, what you end up with is the alpha in the HP minus form is equal to K1 H plus over H plus squared plus K1 H plus K1 K2. And then we can do the same thing and plug in our numbers. And what we end up seeing is that at a pH of 2 and 4 and 6, the fraction that is in the HP minus form is 0.101. At pH of 4, that number actually increases to 886. And at a pH of 6, that decreases to 0.204. This should start making sense because considering that our pK values are given here for phthalic acid, it would make sense that if the pH is really low, lower than pK1, you have this situation where it's not very much intermediate. And when you're above 5.408, it's, again, not much intermediate, but in the middle, that would make sense that the species that's there the most is the one that's in the middle. And then finally, we should take a step through the fully basic form. But if you've made it through this far with the first two, this should be pretty straightforward. So I'm going to try and jump even more steps this time. We're targeting P2 minus. So first we want to substitute out H2P. And so using our combined K1, K2 expression, that should give us this piece. The intermediate, we're going to use, I think the relation between HP minus and P2 minus is the K2 expression. That would make sense. So using the K2 expression, we should have H plus times P2 minus over K2 plus P2 minus equals F. Again, we're going to factor out. And then again, we're going to try and put this together such that our common denominators there, in this case, it looks like the common denominator should be K1, K2. So factoring out, we're going to get h plus squared plus K1H plus K1, K2 over K1, K2 equals F over P2 minus. And that's going to give us our alpha P2 minus is going to be equal to K1, K2 over H plus squared plus K1, H plus K1, K2. So again, we can just plug in. I'm going to fit it up here. pH of 2, 4, and 6. Alpha in the P2 minus form. And when you do this, what you get is at a pH of 2, as you might expect, a very, very, very small number that's 0.000394. At a pH of 4, we've climbed up to the staggering percentage of 3.5%. And then at a pH of 6, that the P2 minus actually takes up 79.6% of the total solution. So this whole process kind of follows the data that we saw back at the beginning with the leucine, where the higher the pH, the more is in that deprotonated form. But we're now breaking free of saying, oh, we have to use K2 to solve for OH minus or H plus, and now we're saying this is H plus, what's everything else? So it's just a different way to look at the same problem. So if we go through that process and we graph it, here's what a hypothetical graph looks like. This is not phthalic acid. This is what your book provided, so I'm going to borrow it, thanks to Harris. What we have is that the major species in solution is a function of what the pH is relative to the pK values. Again, if we were to plug in values, if pH equals pK1, what ends up happening is that alpha HP minus equals K1 squared over K1 squared plus K1 squared plus K1 K2. And in this case, K1 K2 is usually the smaller number because K2 is smaller than K1, and so this value is going to approach 1/2 K1 squared over K1 squared plus K1 squared. Substituting in for the H2P amount, we would get H plus squared over H plus squared plus H plus squared plus H plus times K2. And again, this would tend towards 1/2 with a negligibly small K2. And so that's why you can see if pK1 is 3.02, when pH is about 3.02, pK1 equals pH. The fractional composition of those two substances are about 0.5. Yeah, you can see K2, the alpha 2 minus is down there, so it's not exactly 0.5, but it's pretty close. Of particular note is you can see in this case that the maximum value for alpha HA is far less than 100. You don't have 100% HA minus at any pH, which is kind of interesting to say because that was part of our initial assumption, wasn't it? When you started with the intermediate, you assumed that HA doesn't change very much. I think they're using this information. There's some interesting questions that could be asked about what the fractional composition is at that pH versus what it should be. You think it's 1 and it's not 1 at all, while it has a maximum value. And then again, we can, like I said, these principal species are in relation to pH being greater than, less than, or equal to the K values. Hypothetically, you could do this for a triprotic acid, but maybe, if we're smart, we don't have to do a lot of thinking. Too many buttons. We saw that for the monoprotic acid, the fraction that's in the HA form is equal to H plus over H plus plus K. For the diprotic version, the part that was in the fully protonated form from the previous slide is the H plus squared over H plus squared plus K1 H plus K1 K2. Now, I don't know how easily you all can see it, but if you're careful with it, there are two kinds of people in this world. Those who can extrapolate from incomplete data sets, and from there it kind of expands out. Now, the interesting thing is that for any species, if you can write a solid denominator, you can figure out this formula. Because if you write the denominator in order, that's actually the order of the species, where the numerator for the H3A would be this, the numerator for the H2A minus would be this, the numerator for the HA2 minus would be this, and the numerator for the A3 minus would be this. To put it another way, Harris gives you this general form that if I just kind of threw it at you, may or may not have landed successfully, but hopefully this makes a little bit more sense now. So that if I said, what is the alpha of HA3 minus, considering the acid H4A, it's tetraprotic, hypothetically you should be able to look at that and think for a minute and say, wait, if it's tetraprotic, I'm going to follow the pattern. And I'm going to keep writing because Mr. Mulick has decided to give me a not difficult but super lengthy process. And I ran out of room because I think I just ran into my own head. And since this is the 3, 2, 1, this is the fourth species of 5, we're going to use the fourth term, and that's going to be our numerator. Another way of thinking about this is that the principal species at a given pH is the one that has the largest contribution to the denominator, if that makes any sense too. So looking at our number line, this would be a good way to look at this information. And I'm getting a little ahead of myself with the information that's here, but you can see that the predominant form as you are becoming lower pH and higher pH goes from H3A to H2A to HA to A3 minus. And if you were to graph it, you'd see a similar graph to the diprotic system with, 4 lines instead of 3. Thanks for watching.